This is going to be an interesting video about how to actually drive PMOS MOSFETs. They're really useful because you can put them in the top of the circuit like this. We're going to start with something like this, and we're going to end up over here with something like this. And I even made a little demonstration with a PMOS. A PMOS is different from an NMOS. The PMOS typically you can put between the positive and the load side of things, whereas the NMOS you typically put right here between earth and the load. To turn on a PMOS, you have to create a voltage between the source and gate, which is actually negative. So PMOSs are just reversely intuitive in a lot of ways. First of all, the current flows into the source and out of the drain. I know. And you have to give it a negative voltage for it to become conductive, essentially. And you can try to mess around and with different voltages and stuff, and you'll see it doesn't really work. And that's because this is actually the best way to drive a PMOS, a MOSFET. So the voltage for this, you see the supply is here, so it's not even connected to ground, which it can be kind of a headache. So we can turn this off by giving it no voltage and turn it on, I think probably 8. Yeah, so 8 to 12 to 16 is on, 20 volts you cook it. And you have to actually give it a negative voltage. So that's kind of tricky to do without transformers, isolation, and a lot of stuff. But I'm going to show you a way to do it pretty easily that I kind of just thought of. So using this dorky voltage divider, we can actually kind of trick the PMOS into seeing negative 16 volts between its source and its gate. So you can come down here, and one of the problems with this is you need to use a 20 volt control system. So at 0 volts, the MOSFET's conducting, and at 20 volts, we turn the MOSFET off. And if you can see, now that we have 20 volts, we have no current flowing through this system because you have 20 here, 20 there, no voltage difference. But when this goes to 0, now we have current flowing through this resistor network, which gives us a residue of negative 16 volts right here between the MOSFET's gate and source. Pretty cool. But you say, come on, 5 volts. I don't want to use 20 volts for logic. So we come over here. Now this is the exact same circuit, but you can use 5 volts even down to 1 volt as the control signal. And I think it's uninverted, so we can give it 0 as an input signal, and we have no current flowing. And we can do 1, and now we have current flowing. And that's because we're turning on this BJT, which essentially pulls the whole system down to earth. And then when we turn the BJT off, now no current flows, and once again, we have no voltage on the gate. So this is a useful way you could control 20 volts with like 5 volt logic or something without an operation amplifier or a MOSFET gate driver, just using a transistor and some resistors if you needed to deal with 0 to 1 volts logic. And we can even look at how fast we can switch the system right here. So this is a little sim, and we're going to be probing the control voltage, the gate voltage, and the load current. And I've moved the load from 70 ohms down to 1 ohm, so it's more interesting. This is Circuit Labs. This is the best simulation software ever. All right, so here we see our input square wave from, let's turn everything off so we can look. So here's our input square wave from 5 volts to 0 volts. You could do this with a 5.5 timer, an Arduino. Very good control signal, simple 5 volts. And now we can look at our gate voltage. So here is our gate voltage on top of our input voltage. So you can see the gate voltage, it's floating because it's not grounded. But you can see when we're sending the 5 volt signal, the gate is essentially turning the MOSFET off. And now when we pull the BJT down to ground with 0 volts, or stop pulling down to ground, there we go, words, we can see a little Miller plateau as we switch the MOSFET on. And the difference, if you notice, let's reset our zoom, between the gate voltage and the top and bottom right here is about 21 and 4.2, which is about the 16 volts, the negative 16 volts right here we've been using to drive the gate. And you can even look at the current down here, and you can see the current is now in phase. Yeah, so we have a double negative. So the BJT inverts it, and then we invert it again. So we're back in phase. So when we send the on signal, we conduct current. And you can see we're conducting about 18 amps. And if you come down here, you can see between the off time is 2.625 mils, and it's about off at 2.67 mils, so that's pretty fast. And the on time, which is a little less important, is about 2.125 mils to 2.132 mils, so microseconds, not nanoseconds. In MOSes, I've built a 4 megahertz in MOS driver once, but microseconds pretty good. In MOSes are typically a little faster than PMOS. So I've actually built this circuit over here, and you can see we're using about 20 volts, and this is our control line right here. So right now we're pulling it up to 20, so our PMOS is off, and we can pull it down and turn our PMOS on, which connects this LED. I know it's not a big load, but this is my first time actually ever driving a PMOS in real life, so I thought I would share it with you guys. It's very satisfying. I'm building a solid state switch for work, so it's useful. I love this. You ever just light up one of these LEDs and it makes you so happy? It's so weird. I was trying to explain this to someone last night and they fell asleep. One of my coworkers at work, I was like, do you know about the golden rules of op amps? The current in and the current out, you know? And I look over, asleep. Great. So yeah, I hope you guys thought this was useful. Maybe I should explain this. So this was a 1K resistor. Is this even in focus? Jeez Louise. Okay, so here we have a 1K ohm resistor with our LED, so it doesn't cook at 20 volts. And then we have power right here, which is red. And then right here, we have a 20K, and right here we have a 5K, making the voltage divider, and they're tethered in the gate right there. So the pin all the way to the right is the gate, the pin in the middle is the source, and the pin on the left is the drain. So you have drain, source, gate. And essentially, when we pull this resistor network up, right, no current flows. But when we pull the resistor network down, we generate negative 16 volts between the gate and the source, which makes this very resistive hunk of silicon, phosphorus and stuff, suddenly very conductive. Handy nano engineering. Great. I hope this was helpful, or at least interesting. It was for me, because now I'll never forget how to do this. So anyways, good night. After I recorded this video, I suddenly just realized all these kinds of flaws with this circuit. So it's completely dependent on whether the source voltage is there and the magnitude of the source voltage, right? So this resistor network is tuned for the specific voltage over here. If that was 40 volts, you would cook this MOSFET instead of 20 volts. So that's kind of a weakness. So I put a zener here. So basically the zener makes it so that no matter, let me show you that zener first, right? Right, cooked, 31, cooked, 20, okay, put 16 volt zener in, not cooked, right? The zener clamps it, so it's a good place to put a zener. Zeners are special diodes that just open at a certain voltage. Very useful. In reverse. So anyways, yeah, that's kind of bad. If the supply voltage goes away, you also won't be able to shut down the MOSFET. So that's kind of a weakness, but you don't need a negative source, so I think it's still a great circuit. Okay.